So without further ado, I will just leave the stage to our first speaker, Philip Dolan, who will be talking about photon statistics of single photon sources.
Thanks, Katrina. Hopefully everyone can hear me. And yeah, I'd just like to reiterate the thanks that has already been mentioned. I think the organisers have done a wonderful job, and especially given the ongoing pandemic. So yeah, well done, and thank you for giving me an opportunity to speak about some work that we've been doing at the National Physical Laboratory. This is the UK's National Metrology Lab, and we've been working quite a bit on assessing quantum technologies. So within the talk, I'll go through why we're interested in characterizing single photon sources particularly. I'll talk about the G2 function. This is the second order coherence of photons. And I'll go through this quite sort of slowly so we can all sort of follow along. And then I'll develop this into a model for the third order coherence, which is less often considered. And we'll look at what questions it can answer that perhaps the G2, the second order coherence, can't. So we'll develop a model, and I'll apply that to some early experimental data that we've been taking. Then we'll have some conclusions and summary. So why is the National Physical Laboratory looking at single photon sources? Well, previously we've been working with lots of companies that are working on quantum technologies, particularly in the photonic area for our team. We've been working with the three that I've shown here, and this is on quantum key distribution systems. We've worked towards generating these sort of ETSI group specification documents. So my colleague Christian Allow was a key author in this, and it really allows industry to have a set of standardized tests that they can perform on their systems, which are very new, so they can be sure that the sort of technologies that they're offering are measured in a reliable and repeatable way. And more recently, there's a whole host of new companies that are turning up. So New Quantum, which we already work with, and AGQ, Quandela, Quantum Spiral, and they're offering single photon sources based on single emitter systems. And so similar to these key distributions, we're looking into the future and thinking, well, we need to be able to measure these carefully and characterize them in a useful way for them to turn into a commercialized technology. So what do these single photon sources do? Well, they emit Fox states. So these are states which have a single photon. So we can see the sort of probability distribution I've shown here on the top right graph. But when we're sort of working realistically, you don't often get perfect sort of emitter systems. It might be imperfect in some way, and it can be imperfect in a variety of ways. For example, if it doesn't always give us a single photon, sometimes it might give us two photons, so that the n equals 2 state is populated here. Or it might have a background contribution from a coherent state. And it's important for especially key distribution systems, because the security of the system is dependent on what photons you're putting out. It's important to know which of these it might be. Also, if you were to develop these sources for other applications, for example, to be qubits in linear optical quantum computing, being able to optimize your fidelities and knowing the origin of the imperfection is quite important. So experimentally, we use the G2 function, and this is how we collect data for the second order degree of coherence. So we use a room temperature scanning confocal microscope in our case. We've got a 532 laser here. There's nothing particularly special about this setup. There's many like it in the world, and we use a steering mirror to raster scan our excitation spot around our sample. And our sample is, in this case, nanodiamonds spread across a silicon substrate. So when we scan our laser spot around our sample, we find there's glowing spots, and these are photoluminescence images. So this is where the nanodiamonds are glowing red. And those red photons make their way back through our optical system, this time passing through the dichroic, and the fiber provides the pinhole to make this a confocal system. And for the G2 measurement, we split that light onto 2 detectors. And we use a time tagging method here. So we just log the arrival time with very high accuracy of all of the photons that are measured in this experiment. So we end up with two lists, the arrival times on detector 1 and the arrival times on detector 2. And we simply calculate so we go through our detector 1 list and we find the closest time on our detector 2 list. And we measure the time difference, that's tau, and we histogram that value. So we go through our entire long list and we generate a histogram. And you can see here it's plotted in terms of the number of coincidences. So more than 40,000 on this occasion. This is experimental data we've taken. We then go ahead and normalize this according to this function here. So we divide it through by the length of the experiment, t, the photon fluxes on each detector, and the bin width, so the resolution of what I'm plotting. This normalization procedure has been done many times. And now that we've taken that data and we've plotted it, we want to look at what we can get from that. So what physical insights can we gain? So for nitrogen vacancies in nanodiamond, this paper here has modeled it as a 3-level system. So there's the nanodiamond's considered, well, the MV set of the nanodiamond has 3 distinct levels. We have our radiative path, our optical excitation path given by K12. So that's how we're exciting the system. And it can decay and give us a photon through this K21 transition, but it also has a shelving state. So this 3rd energy level, and it's got a non-radiative decay path associated with it, these 2K rays. So we solve the coupled rate equations to get this expression here. And this is a commonly used G2 function to describe 3-level systems. And if we look at our experimental data, it looks like it might do the job, but immediately there is an issue that for a single photon source, a perfect single photon source, we should never have simultaneous clicks. So our experimental data should ideally reach 0 for tau equals 0. But clearly that's not the case. So we need to develop our model slightly. So we can consider perhaps an additional single photon source. I've labeled this one here B. And we can just consider the pairwise contributions of the photons that we might be measuring in our experiment. We end up with these 4 terms, there's 4 pairs. Some of them are a mixed term, and there's no tau dependence here, because it doesn't matter if A and B they can emit photons simultaneously. We have a sort of G2 function from our second emitter and a G2 function from our first emitter. And this is in contrast to, I might have equally assumed that I've got a coherent background, for example, Raman scattering from my laser from the diamond crystal, or background fluorescence from some organic residue. You can see, if that was my assumption, it's a very similar set of pairings that we make, but there's an important, the tau dependence on my second term here is relieved, because I'm assuming that this is an uncorrelated photon source and they can be detected simultaneously. So, depending on the assumption that I make, I might assume that the additional single photon source is very similar to my first. And therefore I can equate the 2 G2 functions. This allows me to reduce the above expression to this, which was shown in this paper quite recently. I might consider if it's an uncorrelated source, I can cast these probabilities in terms of a relative brightness, and I can write my new G2 function like this. And you'll notice that actually these two have a similar functional form. They're my original sort of photophysics G2 function, multiplied by some constant proportionality with an offset. And the upshot here is that I can fit them both to my experimental data, and you can see they're both plotted here, I promise. It's just that one is exactly over the top of the other. The constants that I get, which fit into my physical model, which correspond to those K rates, they're exactly the same in each case. So you can see that there's a sort of limitation to the G2 function. Depending on which assumption I make, I might consider the additional photons to be from the second single photon source or from these uncorrelated sources. And this experiment alone can't tell us the difference. So we've been working on G3 functions, and experimentally they're quite a simple development. We split light 3 times instead of twice. And this time we record 2 taus where we were recording 1 before. So we have a list of pairs of taus now to plot in histogram. So we do a 2D histogramming. And this is where we increase the value in our histogram depending on the value of tau 1 and tau 2. And experimentally, we get data that looks like this. So this normalization procedure has been reported previously, Matty Stevens in 2014. And it's a similar one. So we divide the histogram by the product of the 3 rates now, and the bin area in terms of like time area, and we get it down to a G3 function. So again, we want to try and find out what's going on here, and we sort of follow the example set in this paper here. So the photophysics of the situation hasn't changed. So we can still assume that the G2 model will have a similar photophysics. But we've got 3 taus to consider now, 3 possible times between the triplet of photons that we're measuring. So we might start with a starting equation like this with the product of 3 G2s, and as this paper showed. But upon inspection, you can see again, this won't quite do the job. If tau1 were to equal 0, I would expect my overall G3 function to equal 0 for every tau1 equals 0 value. And actually, the only 0 bin I've got in my experiment is right at the origin here, where tau1 equals tau2, which equals 0. So this model isn't going to quite do the trick. So we can develop it in the same way that we developed that G2, with the additional photons coming from a second single photon source. And you can see here we consider the 8 different arrangements that you can get for the triplets. And each of them here have a tau dependent. But these extra terms allow us to lift the constraints imposed, and indeed you can get a good fit to this data. Importantly, though, I could have assumed, as before, that my additional photons were coming from an uncorrelated source. And as I've said, for the 2 single photon sources, every term has a tau dependence. But if I assume an uncorrelated single photon source, I have a bunch of terms now that have no tau dependence. And this really is what will allow us to develop this model to distinguish between these 2 cases. So we can fit our experimental data with these 2 models, and you can see the 2 models are plotted out here. And to examine it a bit more sort of closely, it's better to look at the profile of these fits in the off-diagonal. So you can see here I've fitted the full 400 by 400 nanosecond area, but it's useful if I just look right at the origin here, or the central region. And you can see the model give different responses. So the model, assuming 2 single photon sources, agrees with the experimental data here, where we have no 3-fold coincidences in that central time bin. But if I were to have uncorrelated photons contributing to my photon stream, then I would expect a non-zero value here, which is not what was experimentally seen. Now, this is all quite qualitative. The noise on these data sets are quite sort of high. It's a very long experimental duration that we took this for. So we're looking at perfecting our acquisition routes and hopefully dropping the noise in these data sets to get some more quantitative statements we can make. We did check out another nanodiamond. So you can see here, this one is circled in blue, and it's a much brighter nanodiamond. So this is a saturation curve where we start with a low excitation power, and we go up to as high as we can. You can see we saturate out for the blue much brighter, but it's got a worse G2. So we're anticipating many more additional photons, unwanted photons. So we can apply our 2 models, and indeed this time we do get 3-fold coincidences in our 0 time bin. So it's clearly not just 2 single photon sources. But again, because we're fitting over this full 400 by 400 nanosecond region, actually the fit, just assuming uncorrelated photons additions, also doesn't work. So we can blend these 2 models and then arrive at a fit that seems to agree a little better. So that's everything that I've got to talk about. We've constructed a simple approach to incorporate additional photon sources for these statistical models. The G3 can potentially tell us more, I think. We've got to refine the model and get better data to sort of be a bit more quantitative. And these are all with quite low fluxes. So the MV center is not the brightest thing on the market right now. So if we were to start using quantum dots, it might be, if needed, we could look at even higher order coincidences. So thank you for your time. And thank you to Bays, who formed NPL. and I'll be happy to answer any questions.
Hi, Philip. Thank you very much for your talk. We have a question already from Joe Smith asking, thank you for the great talk. I think you said the data took 18 hours to collect. Roughly how many times slower is a G3 compared to a G2 to get similar quality data?
That's it takes a lot longer. So I did do these experiments, and actually, yeah, I mean, similar quality data is the tricky thing there. So I think it depends on what actual rates you're dealing with. So there's not a sort of nice and easy answer, I think, but the main thing is that the scaling is quite aggressive. So a G3 does take a lot longer for these sort of hundreds of thousands of counts in total. So you're talking, you know, over a day to get very, very good data. I think because it scales with the rate so much, I have checked out when you get above a mega count. So some of these quantum dot sources, which are giving you many mega counts per second of photons, it actually opens the door to the G4 as well. So the scaling it does help if you've got more photons per second. But it's a good question.
Cool. Thank you very much. We have another question from Ze Xian Kung. I'm very sorry for pronouncing this wrong. Did you take into account of the measurement setup jitter in the model, as it can affect the deep depth significantly?
You're quite right. So the jitter can. We were using superconducting nanowire detectors here, which had a jitter that we know was around 100 picoseconds, and the resolution of our time-tagged electronics was around 100 picoseconds too. So it meant on this occasion that the jitter was more or less as it was limited by the resolution as much as the jitter. Also, the MB center's got quite a gentle kind of central dip there, so we weren't there wasn't significant deconvolution that would have been required for quantum dots and anything with a much quicker excited state lifetime. You're completely right that jitter does need to sort of be taken into account.
Okay, thank you very much. Questions are flooding in. We have a couple more. A question from Jorge Ruth. Thank you for the talk, Philip. Are these additional photons contemplating dark counts?
So we didn't subtract any dark counts. So again, the SNSPDs have a very, very low count rate, sort of dark count rates, which helps, because when you've got I think it was probably sub 10 hertz dark count rates, that's not an appreciable contribution to these G3 measurements.
Okay, we have just time for one more questions from Peter Koch. If the G3 can be written as a function of G2s, can you calculate G3s from G2 measurements?
That's a good question, and I think the answer is no, because you need the three detectors to simultaneously click to rule out really the two single photon sources or not. But actually, the derivation of that stage of the model we're looking into with quite a bit more depth. So actually, if you've got insights, it would be great to bounce some ideas off you. So I might try and find you in one of these gatherings if that's okay, Peter.
Well, thanks a lot, Philip. I think we ran out of time for now. We have a few more questions, and I will send them to you separately. We'll write them in the chat as well. Thanks a lot.
Cool. Thank you very much.